If r of t is equal to f of t times the I vector plus g of t times the j vector, where f and g are differentiable functions of t, then when you get ready to take the derivative, remember if there's only two components, it's for a plane, but you can take the derivatives of each component separately. If you have a third term, which would be one in space, then it's the derivative of each component separately. Example, let r of t be equal to t times the I vector plus t squared plus 2 times the j vector. The first derivative, the derivative of t is 1, the derivative of t squared plus 2 is 2t, and those will just remain assigned to their locations. So 1i plus 2tj. If we have a vector valued function with a third component, in other words, something representing an object in space, then you can take the first derivative. Derivative of cosine is negative sine t. Derivative of sine t is cosine t. And the derivative of 2t is 2. If we take a second derivative, then we just take the derivative of the components from the first derivative. Derivative of negative sine t is negative cosine t. Derivative of cosine t is negative sine t. And the derivative of a constant is 0, so we lose the k vector component. If we were to carry out an operation like the first derivative dot product with the second derivative, you match it up component with component. For example, multiply the i's, that's sine t times cosine t, the two negatives will make a positive. The j components, cosine times negative sine, and then there won't be a k term. And also, remember, dot product gives you a numerical value, a scalar. So 2 times 0 is 0. And so this dot product is sine t cosine t minus sine t cosine t, which is 0. What does that tell us? That if the dot product's 0, then these are orthogonal. The first derivative and second derivative are still vector valued functions. What happens when we do a cross product? We're going to take the first derivative, cross it up with the second derivative. Remember, you start your first row with ijk. The first derivative, put all of its components in the second row. And then for the second derivative, we'll put those components, don't forget 0 for k, we'll put those components in the third row. Starting with I, ignore the column and row of I, and so you'll take the determinant of these four terms, minus, then you move to the j vector, ignore its row and column, so these four, you'll take the determinant, and then plus k, ignore that row and column, you'll take the determinant of these four items. 0 minus negative 2 sine t is positive 2 sine t. 0 minus negative 2 cosine t is 2 cosine t, but this negative out here negates it. And then finally, sine squared t minus negative cosine squared t. Well, that's sine squared plus cosine squared, which is 1. Remember, with cross product, you get a vector that is orthogonal to the two vectors that you are cross product. To give you a visual, if you were to lay your hand flat on your tabletop with your thumb extended out, like your index finger and thumb, just stretch those out to where they're about a 90-degree angle and keep them flat on your desktop. If you were to put a pencil in that bend where your thumb and your index finger come together, the pencil standing up vertical compared to your tabletop, that's the cross product vector. It's the vector that's orthogonal to the other two. Definition, R of t equals ft times I plus gt times j plus ht times k. That's smooth in an open interval I when each component's derivative is continuous and not zero for any value of t in the interval. Find the intervals on which the epicycloid C curve is given by, and then here's our value, vector valued function on the interval from 0 to 2 pi. We're trying to find out where it's smooth. All right, so we've got our vector valued function. Take the first derivative, that's negative 5 sine t. Don't forget chain rule if you have a multiple angle. So that's going to be positive 5 sine 5t. The next component, 5 cosine t. And then here, don't forget chain rule. It's going to be cosine of 5t times 5. And that'll be your j component. In the interval from 0 to 2 pi, where your derivative is 0 for each I and j component, that occurs every pi over 2 units. C is smooth. Think of it as a 4-leaf clover. On the curve part into each quadrant, that part is smooth. At each quadrantal angle, the derivative will be 0 and therefore not smooth. That's why there's parentheses instead of brackets here. These 7 properties of a vector valued function, and remember, all these documents, you can print these directly from Google Drive or just open them up in Google Drive to refer to them as needed. I'm not going to go through all 7 properties with you. It would just take forever, and these videos are long enough as it is. Let's do an example though. For a vector valued function R, and I'm just going to define it this way, and u of t, this is another vector valued function. It also has an I, j, and a k part. We're going to find each. The derivative, now this is putting those 7 properties from the previous slide to actual use. All right, so we're going to dot these up. We're going to look at the derivative of RT times, I didn't mean to say dot, these are multiplication. But I didn't want to put an X because then it would look like a cross product. All right, so think of it as product rule from back in your Cal 1, derivative of the first times the second, plus first times derivative of the second. Those properties still look familiar. Okay, so what we'll do is we'll take R of t just like it is, recopy it. The derivative of u is going to be 2ti minus 2j, and then because k is a constant, it goes to 0. Plus, then we take the derivative of r, which is negative 1 over t squared, 0, and 1 over t, times vector valued function u left alone. So I'm just going to recopy those 3. Okay, so it's basically product rule. Just take your time and be careful. Multiplying 1 over t times 2t is 2. Negative 1 times negative 2, that's positive 2. ln of t times 0, that's 0. Negative 1 over t squared times t squared is negative 1. Negative 2t, there's no j term here, so that's negative 2t times 0, that's 0. And then 1 over t times 1 is 1 over t. Combining like terms, you get 4 minus 1, that's 3, over 1 plus t. Now, let's look at another property. We're going to take the derivative of the cross product of u of t and its derivative. All right, u of t is given. We calculated the derivative here. So let's take the cross product. Remember that now from that previous page, this is the expansion for this derivative of that cross product. It's u crossed with the second derivative plus the first derivative crossed with itself. Now where there's a nice property back when we covered cross product, and I think it's on that previous page too, but when you cross the same vector with itself, you get the zero vector. So it's mainly just concentrating on this first bracket. U of t, so I'm going to put t squared minus 2t plus 1 in the second row. Remember to always head it up with ijk. All right, so that's vector u's components. The second derivative, now this is the first derivative of u. The second derivative will be 2i and no j. So it's just 2, no j, no k. Carrying out the cofactor expansion for I, it's remember to ignore that column and row. Determinant of these four, which is 0 times I, minus, and then for j you cross out that row and column. It'll be the determinant of these four. 0 minus 2 is negative 2. Negated by this negative is positive 2. And then finally, ignoring the row and column of k, it's going to be k times the determinant of these four items. Well, that's 0 minus negative 4t, which is positive 4t. The I vector had a 0 component, so we just drop it. 2j plus 4tk. Definition, we're going to have the same vector valued function with three components. F, G, and H are all continuous on some closed interval. Then, when we get ready to take the integral, similar to when we took derivatives, you can integrate each component separately. If you have a definite integral, you can spread that definite integral, your lower and upper limits, out to each component separately. So let's jump into an example. We're going to integrate or find the antiderivative of ti plus 3j. Starting with the I term, since it has a variable, you add 1 to the power, divide by the result, so that's t squared over 2i. A constant, you just attach the letter, so it's 3tj. And then a constant of integration. If you have a definite integral, we're going to integrate the vector valued function, which this one's really long. It's got 3 components, but we're going to integrate from 0 to 1. Just be careful to do it each component at a time. So we're going to integrate from 0 to 1. This is t to the 1/3, and that's for the I component. Integrate 0 to 1 for 1 over t plus 1. That's for the j. And then finally integrate 0 to 1, e to the negative t, and that's for the k component. So just take your time, do each one separately. Add 1 to the power, you get, and then divide by the result, you'll get 3/4 t to the 4/3, and we're still going to evaluate that at 0 and 1. For the j component, this is what's the derivative of t plus 1? It's 1. So your derivative, your antiderivative will be natural log of the denominator. Anytime you have derivative over original, it's natural log of the original. To be completely technically right, I should put this an absolute value. It's not going to mess us up in the end that I didn't, but it is a technicality. And then for our k component, the antiderivative, remember, because this power has a negative, it's going to need a negative due to chain rule, because if you take the derivative of this part, you have to get that back. And so we do. Okay, now to evaluate, remember to put your top limit in first, minus your bottom limit. 1 to the 4/3 is 1 times 3/4. 0 subbed in is 0. Natural log of 1 plus 1 is 2. Natural log of 0 plus 1 is 1. And that's our j component. And then now finally for our k component, negative. I chose to leave the negative out. That way I can just strictly do e to the negative 1 minus e to the 0. 3/4 I. Natural log of 1 is 0, so it's natural log 2 of j, of the j component. And then finally, careful here, e to the 0 is positive 1. These two negatives make a positive 1. And then e to the negative 1 is 1 over e, so negative 1 over e. This looks confusing, but it's because I reversed the order when I applied the negative. When I distributed, I actually did second distribution first, first distribution second. Find the antiderivative when given the derivative of a vector-valued function that satisfies the initial condition that r of 0 is equal to this vector in space. All right, so let's start and get our antiderivative. R of t is going to be the antiderivative of the first derivative. So we got the integral of cosine 2t. This will be for the I vector. All right, remember chain rule. This should have a 2 out, but it doesn't. If you put a 2 here, you have to put a half to compensate. So the antiderivative is 1/2 sine of 2t plus a constant of integration. That's for the I component. If you don't trust your integral, or if it's been integration, if it's been a while, take the derivative of this. It'll be 1/2 cosine of 2t times 2. The half and the 2 will cancel each other. Okay, here, the antiderivative, 2 cosine t plus a second constant of integration, and that's for the j vector component. And then finally, this one, be careful. The last example we did was just strictly 1 plus t on bottom, so its antiderivative is natural log. But this one's 1 over 1 plus t squared. That's arctangent, or tan inverse of t, plus a third constant of integration for the k value. Okay, so to satisfy this initial condition, we're going to let t be 0. If t is 0, sine of 2 times 0, that's 0. So c1 will have to be eventually matched up with this 3. This part, if t is 0, what's cosine of 0? 1. So that's 2 plus c2 for the j component. And then finally here, the arctangent of 0 is 0, because tangent of 0 is 0, plus your third constant of integration. Now up here, our initial condition, 0 plus c1 has to match up with 3, so c1 is 3. 2 plus c2 has to match up with negative 2. And that tells us the second constant of integration is negative 4. And then finally, c3 will have to be 1. And now going back to the middle part, the c1, c2, and c3 can now have a numerical value assigned to it. c1, c2, and then finally c3. These problems can be very tedious. Just be patient with yourselves while you're learning this material. Reach out if you need help by email, phone, or stop by the office, and I will do my best to help you out.